Okay, so let's get started. So today we'll start a new topic. We are done with the what we call the concepts and theory part of the course. We started several classes ago with clock synchronization, and we looked at vector clocks, leader election, distributed locks, distributed commit, Byzantine fault tolerance, and then we ended with consensus. Okay, so those are all the key concepts that any distributed systems researcher would need to know when building larger distributed systems. Okay, so we are going to switch gears and come back to more systems aspects of the course. So between now and the end of the class, we are going to go into what I would call case studies or more advanced topics. Okay. So the basic topics are done, the conceptual topics are done. So we'll now start looking at how do you take these ideas and put them into practice. Okay. Today we'll talk about web applications. Next time we'll talk about content delivery networks, a little bit about edge computing, and then we'll look at middleware systems, storage systems, and things of that sort. Okay. There are only a few classes left, and we'll see if there is time to do a few other topics like IoT and so on at the very end. Okay, but we'll see how far we get. Okay, so without further ado, let's start with the today's lecture. So you have all encountered some of these concepts already in the lab or very early on when I was talking about distributed systems architecture. I gave an overview of a few concepts, and here is where we get to look at them in a little more detail. So today we'll talk about principles. Next time we'll get, or maybe towards the end of the class, if there's time, I'll start web caching, but we'll really look at that in more detail next time. Okay. So as you all know, the web is basically a client server based global distributed system. Okay, and typically the web clients tend to be browsers, or they can be applications that run on your phone or other devices, and they access the server component, okay, to typically over HTTP. Okay, so it's a request response protocol that is used by these systems. You send an HTTP request to get an HTTP response. And since all of you just finished your lab, you're very familiar with how all of these things work. Okay, this picture shows a very simple website that's just receiving requests for static web pages, but the server can be a richer web application that can do arbitrary computations for requests that is received, as you did in your lab where you implemented an online store. Okay, and we'll get to some of these concepts as well. Okay, so very quickly, I'll talk about browser clients and servers. So this is a pictorial depiction of a web browser client. Okay, so you can think of any browser like Chrome, Edge, or Safari, Firefox. Okay, by and large, they all have a user interface where the user can submit a request. Okay, the browser will connect to the server, fetch a web page, and render that page. Okay, so in doing so, you'll see that there are different components. There's a UI component for your browser. There's a browser engine. That's the part that's retrieving some of the content. There's a rendering engine that takes the content that has come, whether it's HTML, it decides the layout, it can then embed images, video, and things of that sort. All of that is done by the rendering engine. And then there are other components that do network communication. You might have a client-side interpreter if you need to run JavaScript, for example. Okay, so you will have to run that in the browser. The browser will need a JavaScript interpreter there. Okay, and then you have the parser that can parse HTML and so on. So the client itself is a complicated application, okay, and it's basically always talking, in this case, to a server. Okay, now the server itself also has many components, and all of you have written a very trivial web server or used an HTTP library to implement one. So you kind of know what is in the server, but here's an architecture of what the Apache Web Server looks like. Apache Web Server is the most popular web server that is used on various websites. Okay, it has comes in multiple flavors. Okay? The original Apache Web Server, okay, came as a multi-process architecture. Okay? And then other variants also support multi-threading. Okay? All the concepts we talked about, the thread pool, process pool, they're all implemented in the Apache Web Server. By default, Apache will use a process pool architecture. When you start it up, there will be a primary process that is listening for HTTP requests. When requests come, it hands it to one of the child processes. Okay. You can also have a multi-threaded architecture. Neither of that is shown in this picture, by the way. This is actually what happens after a request is received. But just to finish what I was saying, if you use a multi-threaded architecture, there's a listener thread that's listening for requests, and then there's a dynamic thread pool that can grow or shrink based on the load, which is going to then service those requests. Okay. Now, once a request is received and it's being processed, this is the architecture, regardless of whether you use a process-based or a thread-based architecture. Okay. So this might look complicated, but essentially the way to think about this is it is a modular architecture that used pipelined processing. Okay. So requests come in and they are going to essentially undergo processing by various modules that you can plug into your Apache Web Server. Okay. And there are all kinds of modules that are supported. So you can have a PHP module that can do PHP processing. It can actually look at PHP requests and process them. You can have SSL modules that will listen to secure connections. So all kinds of modules are supported. So it's an extensible modular architecture. So you will see that there are modules that you can plug in when you start the server up. And then when requests come in, essentially they undergo pipeline processing through these modules and the response is generated. Okay. This is only doing HTTP processing. Okay. We'll get to how you can actually write code and do other kinds of processing in there. Okay. The only kind of processing that is supported in the server itself is if you write your application using PHP. Okay. Instead of using simple HTML, you can also have PHP language, and that can be supported by the application itself. If you write your application in Java or Python, as you did for your lab, then all of that processing is happening outside the HTTP server. This part is only doing HTTP processing, and then the request will be handed to another component. Is that clear? Okay. All right. So I'll introduce one more concept, and then we'll start looking at details of web application. Okay, so the concept I want to introduce here is one of a proxy server. Okay, a proxy server is an intermediary that sits between the client and the server. So the client server architecture becomes a client proxy server architecture. Okay, so here you have a proxy, so that's your client. There's a browser, there's a proxy that's sitting between it and the server, and the proxy is responsible for a number of things. Okay. In this case, in this example, it's showing what is called protocol translation. Okay. The proxy is exposing an HTTP interface, but then it's converting the HTTP request to the FTP request that the server supports. Okay. So here you're essentially doing language translation. Okay. But proxies can be used for any number of things. Okay. Typically, a proxy can take over some responsibility from the actual server. Okay. And proxies can be deployed closer to clients than the actual server. So requests come to the proxy can handle the server, you can send back a reply immediately. Okay. The proxy cannot support, or not support, but rather process that request, and it will send it to the server for processing, as you can see. Okay. So proxies can play different roles. Okay. The one that we are going to look at, not today, but most likely next class, is one where proxies are used for caching. Okay. Proxies can cache content from the server. Okay. In that case, the server is an HTTP server, regular web server. Okay. Proxy caches content that has been retrieved from the web server. It maintains a cache. Requests come in, you look at the cache. The content is already cached. You can reply immediately. Okay. This will reduce the response time for requests because the assumption is proxies are closer to the end client than the server. The server may be a machine somewhere in the cloud. A proxy could be a machine somewhere on your network, as an example. Okay, so that's one of the reasons you have proxy servers, and we'll come back to this next time in more detail. Here, I just wanted to introduce the concept of a proxy that sits between the client and the actual server. Okay, so with that, let's now talk about web application. Okay, so our client server architecture has a server, but the server itself can have many components. Okay, we already looked at this multi-tier concept in lecture 2 or lecture 3. Okay, today we'll look at it in more detail. Okay, so here's a standard 3-tier architecture for your web application, where the first tier, okay, is an HTTP tier. All the HTTP requests are coming to the HTTP tier, so there's HTTP request handling. Okay, the next tier is your app server. Okay, this is an old figure that shows a very out of date way of writing these applications using something called CGI, just common gateway interface. So you wrote application using scripts. You no longer do that. Okay, what you do is you write your application in a modern programming language like Python or Java or Ruby on Rails and things of that sort. Okay, and so that is where your code is going to sit. It's going to do processing, and there is often a database tier or a data tier where the data for your application is stored. Okay, pretty standard 3-tier architectures. Requests come in and they flow from the first tier to the back tier. Responses go backwards. Okay, now in our context, as we will see maybe next time, okay, the server itself, okay, I already said the proxy can have a cache, okay, to cache content. Okay, there is often caching even on the server side. This is server side caching. Okay, so for example, you can cache recently retrieved queries at the app server. So rather than making a query again, you can basically say, was this query already made previously? If so, you already have the query results. You don't have to go to a database because IO requests are slow. Okay, so even here you can introduce caching in this architecture, which you have not seen before, but something that we'll look at as well, okay, to improve performance. Okay, so now let's look at making that architecture more sophisticated. You already know how to make a multi-tier application. You actually wrote a simple one in your lab, okay, already. So how do you scale this architecture? Okay, one way is to actually cluster your web application. So in this case, you take your web application, okay, and you run it on multiple servers. Okay, and you're going to put a front-end machine that is essentially going to receive all the requests. And then those requests are going to be sent to one of those web servers. Here, by web server, we mean the entire web application, okay, that I showed you on the previous slide. Okay, so the clients are going to connect to the front-end dispatcher, which is going to forward requests to one of the replicas. Okay, and we have seen this picture before when we talked about cluster scheduling. If you remember, okay, there was a little bit of discussion we had where we said you can essentially have a web cluster. Okay, so this is one common way to scale your application. Okay, if your single machine is not enough, okay, you're going to replicate. Okay, so this is how you're going to actually replicate your web application. Okay, each of those boxes that is labeled web server could be your entire multi-tiered web application that you put there. Okay, so you can have multiple tiers. So that's a logical box, okay, that can actually have multiple tiers in each of them. Okay, and there are many architectures for this. I will show you a picture that I drew in just a second. Okay, so here are two ways you can implement this. Okay, in this case, you have the load balancer. Okay, that's essentially receiving HTTP request. It sends it to one of the app tier replicas. Each app tier replicas have their own database tier. Okay, so in this case, the app tier is replicated, the database tier is replicated. The HTTP tier is essentially in the load balancer. It's simply receiving HTTP requests and forwarding. Okay, this is one architecture. Here's another architecture that's actually even more common than this one, where the load balancer receives HTTP request. It sends it to one of the replicas, which is on the app tier. Okay, and then the app tier has a common database tier. Okay, so all the database queries go to a single component. Okay, just 1 second. Okay, so you can think of these two. Both of them allow you to scale up because the app tier or the application request processing is replicated. In one case, the database is also replicated, but in the other case, it is not. Okay, so the question is, when would you use one or the other? What's the advantage of not replicating the database or a disadvantage of not replicating the database. Yes. Right. Okay. So the reason many applications don't replicate the database is because if you replicate a database, you have to synchronize the data. Okay, that's a complicated problem because if you then you have a replicated database, every time an update is made to one of the copies, that update has to be sent to all others and so on. Okay, so it is much better to put a big server and put the database on a large, well-provisioned server and just replicate the app server. Okay, so that's a common way by which you can scale up, so long as your bottleneck is not I/O. Okay, this is going to be fine. If your bottleneck is I/O, then doing this doesn't help because the bottleneck is in the database tier. So then you can't really put more replicas here and scale up your throughput. Okay, but in many cases, the request processing is where the bottleneck lies. Okay, the code. So in which case, if you actually replicate this tier, then you can scale up the application capacity, but you don't need to worry about replicating the database and making it synchronized and so on. Okay, synchronizing the replica. Okay. In the first case that I have here, okay, you're actually replicating the database tier. If your database is updated frequently, then you have to make sure the copies are all synchronized, otherwise they'll be inconsistent. Okay. Often this is used for databases that are mostly read heavy and only infrequently updated. Okay, so let's say in the store, you can have a product catalog. Okay. Maybe you don't actually keep the stock information, but the product catalog just has the title of a item and the price. Okay, that's not going to be updated frequently because the store may not change its product catalog frequently. Okay, so you can actually afford to update your you can afford to replicate your database tier because it is not write heavy. So you can periodically just do batch updates of the databases and have it be synchronized. Okay? That still allows you to then replicate your database tier and potentially distribute it in many different locations. This is not going to work if your replicas are distributed. They all have to be in one location. But that will work if the first replica is in one location, the second replica is in another location, and so on. Okay, so there are many trade-offs here that you have to keep in mind. But for now, you can just assume this as the simple way you can scale applications without having to worry about database synchronization and things of that sort. Okay, any questions? Okay, all right. So there are many ways by which the load balancer can actually forward request to one of those web servers. Okay, there are in fact 2 or 3 different ways this can be done. I'm going to come back to this picture. I'm going to explain how that is done first. Okay, so the first question you have to ask is load balancing done on a request basis or a session basis? Okay, in a request basis, every HTTP request that is coming in can be potentially sent to any of the replicas. Okay, this is request level load balancing. Okay. In a session level load balancing, the browser creates a session with the web server. Okay. Once a session is established, it's mapped to one of the replicas. All requests of that session are sent to the same replica. Okay. So each browser's session is then going to be mapped. So if you send another request, it will not get sent to another replica. It will get sent to the same replica. Now, there are many reasons you may want to do session level load balancing as opposed to request level load balancing. Okay, what are some of those reasons? Yes. Okay, you can use a cache. That is true. It will help you. Any other reasons? Okay, caching is one. Anything else that you can think of? Yes. Okay, so you're saying if you have multiple databases, then you can just keep sending it to one database and update them. A better way of saying that is state is actually then kept at a single location. So suppose that you are implementing a web application that's an online store. Okay? So a user might say, I want to put this item in my shopping cart. Okay? A shopping cart is state for that client. It's kept at the server. Okay? If your server is replicated, okay, that shopping cart state will be in the memory of one of those servers. Okay? If I did request level load balancing, okay, I can put an item in the shopping cart, and in the next request might be buy this item. If that goes to a different replica, that replica doesn't know what has happened before. Okay? So it is important that all the state of that session is actually kept at a single machine. Okay? This is one of the reasons why you are going to use session level load balancing for many of these services, not request level load balance. If you are stateless services where no state is kept, then you can do request level load balancing. There's no reason to do session level load balance. But if there is client specific state that is stored at the server and specifically in the memory of the server, then you have to do session level load balancing. Okay? The only way around that is to then actually take that state of the client and put it on a common disk where any other server can also access it. If you keep your shopping cart on disk or in a common database, then you can send that request to another machine and then it can still retrieve it and get it back. But if you keep it in memory, you have to do session level load balancing. Okay? So these are two approaches that are used, but regardless of which approach you actually use, the way the load balancer can actually forward requests to one of the replicas is you can either use HTTP redirect, you can use something called TCP slicing, or you can do something called TCP handoff, which is like HTTP redirect. Okay? So what do these things mean? Okay, here's a client. Okay, and then that is essentially your load. It's a complicated figure, but you only need to worry about actually three things here: the client, the load balancer, and the web server. So client has made a HTTP request to this machine. Okay? But the actual machine that is serving that HTTP request is some other machine. Okay? So how is it going to send that request? Okay, one way is to use what is called an HTTP redirect, where this machine is simply redirecting the HTTP request there. So that server will then service the request and directly send a response. Okay? So that's called a redirect mechanism. So your load balancing switch is just acting as a redirector. It's one approach. Okay. Second approach is what is called splicing. Okay. So you basically make a request to the switch. The switch takes that request and makes a second request to that one of the replicas. Okay, response comes back, it takes that response and it embeds in the first request and sends it back. So essentially, there are two connections that are spliced together. Okay, so this is called splicing. Okay. And the third is called TCP handoff, which is like HTTP redirect, where you get a TCP connection for an HTTP request. You essentially hand off that TCP connection itself to another machine. And this requires you to do some additional network level, add network level mechanisms where you make a socket connection to one machine. That socket connection is essentially handed off to another machine. So you have to use one of these multiple mechanisms for that forwarding to work. The simplest one, as I said, is simple HTTP redirect, where you make an HTTP request, it's just handed off to another machine. Okay. So these are all details of how some of these low-level things work. Okay. So you can use one of these mechanisms, and different types of load balancer use different mechanisms. Any questions on this? Yes. And which one to use? So the question is, can you give use cases for it? So they all do the same thing. They take an incoming request and they hand it off to some other machine. The question is, which mechanism should you use? There are multiple that have been developed. Okay, they have some advantages or disadvantages, but they all allow you to take a request and send it to some other machine. But the client actually sent a request to the front end switch. It may not even know the presence of some of these web servers, right? So if you do an HTTP redirect, all of those replicas, okay, that I showed you, they must all have a public IP address, because you're essentially sending your request, redirecting the request to one of the servers. The server sends back a response. Okay. But if those machines have a private IP and only this switch has a public IP, you cannot use HTTP redirect, because the server may not actually have a public IP. In that case, you might need to use splicing or a handoff to do something, right? So there are pros and cons, but by and large, they all allow you to do load balancing of either request or session. Your question?
So adding to this question, so I think that the HTTP direct has no session information, but the other two should have session information. So the other two, by issuing a request, I don't know which topic is created for which line, so I can use the same topic each time. But HTTP direct might not require this. I will just forward the request.
Right. So question is, will HTTP redirect have session information versus other things, right? So first of all, I did not actually explain mechanisms by which session information is kept. Okay, whenever a client, so there will be many clients that are accessing the web server. When any client sends a request to the switch has to keep a table saying, I received a request from this client. Okay, is this part of an existing session? If so, you look at what machine it has been mapped to, and then you take that machine, and then you can use any of the techniques. You can do an HTTP redirect to that machine. You can do a TCP splice or a handoff. Okay, so how you keep the state of a session and which technique you use are somewhat orthogonal. They are not necessarily the same thing. Okay? Having said that, to some degree, there are schedulers that are simply going to do an HTTP redirect, and the client can then send subsequent requests directly to the machine. In that case, you're right. Right? So, but that is not what I was talking about. I'm assuming in this picture that all requests first come to the load balancer and then it is simply forwarded. Okay? In that case, you can just keep some session information and then forward to the right machine. Yes, question.
Maybe I did not be able to do this work. I had to hand over this to some others. But now there is already open source.
So okay, so you are asking, suppose I receive an HTTP request, I do some partial processing and figure out that I need to send it somewhere else for subsequent processing, right? And then can you do it? So if you think about it, your multi-tier architecture, microservice architecture, they all do exactly that. Okay, so request comes in, each tier or each service is doing partial processing, and then it's making another request. You don't actually have to hand off the request. You can simply make a new request, get some results, and then relay the response back. So it. Right. So if you're asking, how do I actually ask a client to forward all its subsequent requests to another server, there are other mechanisms to do that. But in the first case, if you've done some partial processing, you can still do an HTTP redirect. There's nothing that prevents you from taking the original request and forwarding it. That's not a problem, because you just haven't sent a response yet. Right? So that is still possible. Okay, you had a question? Yes, so in HTTP redirect, you basically get a new URL effectively to talk to. Okay? In TCP splicing, you essentially have the request already. You make another connection and you relay the request. Okay? And TCP handoff is doing something similar. Okay, so these are a few different mechanisms to do load balancing. But let's move on to some other interesting techniques that you can implement when you have a clustered web application. Okay? This one is called elastic scaling. Okay, so what is this technique and what is it used for? So first thing you want to keep in mind is when you deploy a web application, okay, and let's say you put it on a cloud, the workload it is going to receive, okay, from its clients or users is going to vary over time. Okay, there'll be times when the workload is high, other times when the workload is low. Okay, so web workloads show time are time varying and they see temporal fluctuation. So for example, they will see what are called time of day effects, where the workload is higher during the day and less during the night, simply because there are more users accessing that web application during the day than the night. Okay. There may be seasons where the workload is higher than other times of the year. Okay. So if it's online stores, whenever there is a sale, you will actually have a higher workload on your application because there are more users trying to buy things from your store. Okay. So web workloads can see all kinds of variations over time. Okay. And then there are other kinds of workload dynamics, which are called or flash crowds. So in this case, the workload seen by the applications increases suddenly without any advance warning. So this can happen for any number of reasons. So for example, news story breaks, big news story breaks. Everybody goes to their favorite website. That website suddenly sees a huge increase in traffic. Okay? That's an unexpected event. Okay, but there are many other types that are expected. For example, there's a popular sporting event and it's the final game of a soccer match, or maybe it's the Super Bowl. Okay, so you expect that any sports website is going to have much higher traffic than other days. Okay, or Black Friday. Okay, that's the time when every website sees a huge increase in traffic because there are big sales on those days. So there are these kinds of effects that this web application sees. Okay, so then the question is, how do you design your web application so that it can deal with all of this changing workloads? Okay. One approach is you decide what is the absolute maximum workload your application will see and put enough servers to serve them. Okay, so you say, even on the worst day of the year, this is the peak traffic my application will see. It needs 10 replicas, so I put 10 replicas. Okay, so that's something you can do. Now, it may be that those events are rare, so most of the time only 1 or 2 replicas are actually seeing traffic and the others are sitting idle. Or you may actually not be able to predict what the maximum traffic is. How do you know how many users are going to come on your Black Friday? Maybe you have a product that's in high demand and maybe you don't have, right? So you cannot tell ahead of time. Okay? So as a result, what happens is applications are often under provisioned, where the workload actually exceeds the capacity of the application, even when it's replicated. Okay? And the website just gets overloaded and stops working. And you may have seen this in many cases where on certain popular times, website doesn't work, right? Spire doesn't work during registration days often. This happens even after 10 years of Spire. Okay? So and that's the day when it's seeing actually a load spike. So even though there is replication and clustering, this still happen because they under provision the system. So what can you do? Okay, so this is where this notion of elastic scaling comes up, where you increase the capacity of your application on the fly when the workload increases. Okay, this is called auto scaling or elastic scaling. So it's not that some human is sitting there and saying the workload has gone up, the machines are 90% loaded, so let's add more capacity. Okay, you want the system to do this automatically for you. Okay. So this is called elastic scaling, where the web cluster is monitoring its incoming workload. And whenever it sees that its replicas are approaching some threshold capacity, you will start adding more servers. Okay. So you can do this in the cloud programmatically, because in cloud, you can just make an API call and request more servers. Right? So what you will do is your load balancing switch will monitor the workload, and if it sees that those servers are getting overloaded, it'll just make a call to the cloud platform, get more machines, okay, start new replicas on those machines, add them to the pool, and now you have suddenly increased the size of your cluster on the fly. Okay, and this can be done in order of minutes. You don't have to wait for hours for some human to take action. Okay? So this approach is referred to as elastic scaling. And there are many flavors of elastic scaling. One is called horizontal scaling. Horizontal scaling means you vary the number of replicas as the workload goes up or down. If it goes up, you add more replicas. If it goes down, you terminate some replicas. Okay, it's called horizontal. Okay. Vertical scaling is also a type of elastic scaling where you don't change the size of the cluster, but you can make the replicas bigger or smaller. Okay. So on the same machine, if there's idle resources, you can give the virtual machine or container more cores, so it just becomes bigger. Okay. Or you can reduce the number of cores, reduce the amount of memory, and so on. So this is referred to as vertical scaling, where you change the capacity of each replica rather than the number of replicas. In either case, you are making your application have more capacity so it can serve more requests, either by adding replicas or making the replicas bigger. Okay. So these are two popular approaches that are now commonly used in cloud applications. If you deploy an application on your cloud platform and you don't know the workload that it can see, the peak workload that it can see ahead of time, you just essentially turn on elastic scaling and let the system deal with it for you. You don't have to guess what is the peak workload. And then when the peak workload exceeds your cluster size, on registration day, you can't access Spire. Wouldn't it be nice if it scaled up and you could do it, right? So that's how you want your applications to behave. So that is what more modern web applications or cloud-based web applications will do. Okay. And there are many details that I have not mentioned here. One of the details is when do you do the scaling up or down, regardless of whether it's horizontal or vertical. Okay. The proactive approach says try to stay ahead of the workload. Okay. Look at the workload trends and predict what the workload is going to look like in the next hour. Okay. And then based on that prediction, pre-provision extra capacity. So the machines are already provisioned even before you actually hit the capacity. Okay. That's called predictive or proactive scaling. Okay. The other is reactive. Reactive says you don't do any prediction, you just watch what is happening and react to it. If the workload hits 70% or 80% capacity, start provisioning servers. Okay. But there may be a sudden spike and you may actually need some extra time to provision the server. So there may be some short-term disruption. In either case, you are adding capacity on the fly. Okay. So if you actually look at cloud APIs, you will see that most cloud platforms will allow you to add this auto scaling features without a whole lot of changes to your code. Your code can stay the same so long as it is replicable. You can create new replicas and add to it and so on. Okay. This is called elastic scaling. So this is how you build your modern applications to react to your workloads on the fly. Any questions here? Okay. So with that, let's talk about microservices. Okay. So most of you should be familiar with what they mean because you implemented this in your lab. Okay. So microservices is a way of writing distributed web applications where the functionality of your application is split up into small services. Okay. That application tier that I showed you in a multi-tier application, okay, is no longer one component, but in a microservices architecture is a set of components. Okay. Each is called a microservice. Is the question? Yes.
You are not sharing the slides.
Oh. Okay, hold on. I don't know why the slides are not being shared.
And then realize.
Okay. Okay. I think there was a mistake. I don't know why it stopped sharing. But anyway, let's come back to the microservices architecture here. So what the microservices architecture says is take a multi-tiered application, take the application tier, okay, which is typically a monolithic application tier, and splits it into smaller components, each of which is called a microservice. Okay. This is also an example of a service-oriented architecture, but we don't need to worry about it. Okay. The reason you want to do this is modularity. Okay. You can actually make modifications to each service independently of others. Okay. So you don't need to look at a very large code base to make small changes. You can, if your application is split into smaller services, each of them have a very clean interface, you can make local changes without impacting the rest. So it is easier to manage. Teams can be responsible for one service and not have to worry about how you can make a modification. So long as the interface doesn't change, you can change internals to it and so on. Okay, so each microservice is small, it's maintained independent, can be maintained independently of others. More importantly, okay, it can be independently deployable, which means you can take one version of a microservice and swap it out with an updated one without having to bring down the entire application. Okay. So you don't have to take the whole thing down and deploy. You can deploy each one independently. Okay, and most importantly, each microservice can be independently clustered and auto scale. So you can say this microservice is compute intensive, so I'm going to make 5 copies, 5 replicas of this. That one is less compute intensive. I only need 3. Right? So rather than taking the entire app tier and making n copies, each service can be independently clustered. It can be independently scaled up or down. So all of these advantages come to you. Okay? But it does make your application look more complex because there are all kinds of microservices. You may have 20 microservices in an application or 100. Right? So it does make it look more complicated. But from a maintainability standpoint, each service can be maintained independently, deployed independently, scaled independently, and so on. Okay? So that is our microservice architecture. And you already implemented a simple one for the lab. Okay? But the important thing you want to keep in mind is that it is one more way to scale your application. Okay? So this is a 3-dimensional cube that shows 3 different ways of scaling web application. Okay? So the x-axis is called horizontal scaling. We already saw that. You basically keep adding replicas and they don't have to be automatically added, but you can still keep adding them manually if you want. That scales the application capacity. Okay? Add more replicas. That's the x-axis. Okay? So the z-axis is called data partitioning. So this says instead of replicating your data, you can partition your data. Okay? That's an architecture I didn't show you. So if you don't want to replicate your database tier, but it becomes a bottleneck, one way is you split the tables and you put some tables on one replica, other tables on another. Or you take the tables and you partition them. You say all usernames from A to S are on one machine, all from the rest are on another machine. So you literally partition the data and you split it. Okay? Then you don't need to worry about synchronization. You essentially sharded or partitioned your database. Okay? So that's called the data partitioning way to scale. The y-axis is called functional decomposition, where you take the code, you split it into microservices, and you scale them independently. Okay? And you can use any combination of them. Right? So these are 3 different ways you scale an application. Typically, you will use some combination of all 3. You will have microservices to split your code. You will have horizontal scaling to scale your each microservice. And you may use partitioning because you don't want to deal with the hassle of replicating your database and synchronizing it. You would rather partition it. Okay. So these are 3 common techniques you will see when you design large-scale web applications, okay, to scale them. Yeah. Any questions here? Okay. So with that, let's talk now about HTML and HTTP. Okay. Most web applications, as you know, or not web applications, rather web browsers. Okay, when they go and make an HTTP request, they're going to get back content. Okay, typically, the content is going to be an HTML page. Okay, that HTML page might have embedded objects that could be images, audio, video, and so on. Okay. So what this slide is showing is essentially the different types of objects or content you can retrieve from a web server. Okay. So the simplest one is text content, okay, of which you can, of course, get plain text file, but the most common one is HTML files. Okay. You can also get XML files, as we will see when we talk about web services. Okay. You can get image files, you can get audio, video, you can get other kinds of arbitrary binary applications like or even PDF files, or you can have multi-part file. Okay. So when an HTTP request generates a response, okay, that response is going to have this content in it. Okay. And the content is encoded using MIME, just as you have. MIME is a way to encode that content, and just as you have attachments in email, those are MIME attachments. So do you have attachments in HTTP responses, which could be any of these. Okay. So web browsers will then extract this, then they will parse it and then render it. Okay? That's how essentially those are how the kinds of objects that you can have in web document. Okay? So with that in mind, let's talk now about HTTP server and then how you can make the HTTP protocol itself better in web application. Okay? So what this figure is showing is a very simple client and a simple server where the browser is making repeated connections to the server. Okay? So in the simplest case, every time a browser makes a connection to a server, it sets up a new HTTP connection. Okay? So let's say, for example, you connect to a web server, you get an HTML page. You look at the page, there are 3 images in that page. Okay? To get each of those images, you have to now make a new connection, get each image, okay, in turn. Okay? So each entity or object you are retrieving from the server has its own connection. Okay? So you incur the overhead of setting up a TCP connection, sending HTTP requests, getting a response, and so on and so forth. Okay? And then once you get a response, you tear that HTTP connection on. So it's called a non-persistent connection. Okay? The connection lifetime is simply send one HTTP request, get one HTTP response, connection is shut down. Okay? This is how HTTP version 1 worked. Okay? Then people said this is wasteful. Every time I make a connection, I'm setting a new HTTP connection. If I then subsequently send another one, why do I need to set it up again? Could I not have reused my connection? Okay? That gets us to HTTP version 1.1, where connections between the client and the server are persistent. You set up a connection, you send one request. Okay? You get a response. If you want to send another request to the server, you keep that socket connection alive, send the next HTTP request over the same socket connection. Okay? And so on. Okay? The only thing to keep in mind is those requests are sequential. Okay? You have to get the previous response before you can send the next request. Okay? So if you download an HTML page and it has 3 images embedded in it, okay, if you want to use persistent connection, you will have to get those images sequentially. You have to get send the first request, get image 1. Then you send another request, get image 2, and so on. Okay? Now this can be slow. So many browsers don't use this mechanism, because if you want to download multiple images, you would rather set up 3 connections and download them in parallel. That will actually get the page faster and allow the user to see faster rendering of the page. Okay? So even though you can actually persist the connection, when you want to make multiple simultaneous downloads from a server, browsers would rather set up multiple connections and fetch them in parallel, just as you had here. You can set 10 HTTP connections, get 10 things in parallel, okay? Because getting them in parallel is faster than getting them in sequence, assuming you have the bandwidth to do so. Okay? So HTTP connection 1.1 had this notion of persistent connection, but because the connections had to be made, or the requests had to be sent sequentially, didn't really work, didn't achieve the goal of what they were trying to do, which was to save the connection overhead. Okay, and we'll see how HTTP 2 solved that problem. But before we do that, just wanted to sort of put up some very common HTTP methods. Again, so you've seen some of this in your lab. So the most common one is called a get HTTP request. These are types of HTTP requests. In get, you're simply sending a URL and then fetching whatever that URL is pointing to. If it's an HTML page, you'll get a page. If it's a JPEG image, you'll get the JPEG image. If it's a REST interface, as you saw, that URL actually triggers some code and generates a response. Okay, so that's essentially get. Okay, put allows you to actually store a document. Post allows you to add data to a document. So whenever you submit web forms, okay, or using a web browser, and you hit submit, that essentially goes as a post request. Okay? And when you're trying to retrieve something, you send a get. So get and post are the most 2 common types of HTTP methods. Okay? Delete allows you to delete a document, but most web servers will not support it. They won't let some arbitrary client come and say delete some content and start deleting. Okay? But it is part of the protocol. Okay? And put is actually used to upload documents. Again, it is used only when you're using it to upload some files from your machine. But if you're submitting web forms, you're going to use post. Okay? So these are common HTTP methods. developed maybe 25 years ago, but still the most basic methods are still the same in HTTP. Okay. So with that, let's see how HTTP2, which is the most recent version of HTTP, has solved some of the problems of HTTP 1.1. Okay, HTTP 1.1 introduced the notion of persistent connection, but it required that each connection or each request is sent only after the response to the previous one is received. So it was essentially sequentializing. You cannot send the next request while the previous response is outstanding. Okay? HTTP version 2 is designed to address the message latency problems, but gets rid of most of these issues. Okay? So first thing, so there are three main features there. First is it allows you to have binary headers, not textual headers. Okay? So HTTP assumes that the headers are all textual. Okay? Here you can make the headers binary and then you can compress them. Okay, so essentially, rather than sending text strings, you can send compressed version of text strings, which will make the message smaller. Okay, so then it will be faster. Okay, so essentially you add compression to your messages to make them smaller and hence faster. Okay, that's one. The other more important thing is it allows concurrent connection. It is persistent connection, but with concurrency. You can send multiple HTTP requests on the same connection even without waiting for the responses to come back. Okay? The way you do that is you introduce the notion of a stream. Okay? Each stream is one request and one response. Okay? So you can have multiple streams in progress. If you want to send a new request on the same connection, you say this is a new stream, this is stream 5, you send a request. Okay? And then when response for stream 5 comes, you know what request it was for. So each request is basically its own stream, it has its own ID. So you can have multiple of them outstanding. They can come in arbitrary order back. They don't have to come sequentially, but you don't have to wait for the previous response to send the next request. So you can actually send them all in parallel. Okay? This is going to speed up your connection significantly. You don't have to set up multiple connections. Okay, you can use the same connection and send as many requests as you want without waiting for the response to be received. Okay? So this actually is an important innovation that has allowed browsers to significantly speed up HTTP performance. Okay? Note that the protocol itself hasn't changed. It still does get put. All of those still are the same. The only thing you did is you compress the request, okay, so that you can make the messages smaller, and you reused your socket connection, so you don't have to set up lots of socket connection to the same server. Okay, so this is going to give you performance improvement. So it's purely performance enhancement. There's no protocol enhancements in terms of new functionality. It's just improving performance. Okay? But all modern browsers allow you to use HTTP2. Okay? This is not backward compatible. Okay? Both the client and the server have to support HTTP2, because if the server is sending you compressed data and the client doesn't understand HTTP2, it won't know what to do with it because it's assuming textual information. So both endpoints have to support it. So it's not backward compatible, but if you have both sides doing it, you'll get much better performance. Okay. So Google was the company that came up with this. They introduced this in Chrome and others. Now most browsers will support it. Okay. If you have more interest in this, there's a URL there. You can actually read up about all of this in more detail there. Okay, so that's HTTP2. So with that, we can now talk about web services and REST and things of that sort. Okay. So what are web services? Web services are a way you can write web applications and use RPCs between these applications. Okay. So web service is a way to use RPC between a client and a server, or two machines that are essentially doing RPC. Okay. Now, when you use the term web service, it has a specific connotation where you use a certain type of interface description language, use a certain type of protocol for SOAP for you to essentially send RPCs. Okay? So what you do is you say the server is exposing these RPC methods. You write it in an interface definition language called Web Service Definition Language, WSDL. There's a compiler that's going to generate stubs for both the client and the server. So you will see the client stub, a server stub. Okay, then you use that to write your application using these stubs. And then the protocol that you use to communicate is SOAP, which is like HTML, except that's an XML-based language. So you're using, just think of it as RPC calls that are basically going over XML. All the data is and the responses are going as XML requests rather than binary requests. Okay, so that is what web services are. Okay, and I'm going to show you some examples of what that requests and responses look like. Okay, so SOAP stands for Simple Object Access Protocol. Here's an example of making a RPC request over SOAP. Okay, so you will see that it essentially says the RPC request is like an URL that is mentioned there, example.org alert control. It can have arguments that you can put in there and so on. Okay, here is essentially the message you want to post as part of that alert. So that's the argument string that you're sending. Okay, so this entire request is essentially going as an XML document from the client to the server. The server will parse it, say that's the method name. These are the arguments to the method, and it will invoke the method. Okay? So essentially, in RPC system, you've seen how RPC systems work, but you're using SOAP and XML rather than some binary buffers that you're sending and so on. Okay? gRPC uses protobuf. Here, you're essentially using XML. Okay? That's essentially what you want to keep in mind. Okay? Now, here is the okay, your question is. Okay, question is, while you're communicating between microservices, will you use HTTP2 or HTTP1? To some degree, that depends on what the HTTP library does, because it's transparent to the client and the server. You are just constructing the standard HTTP GET request. Now, before it is sent, will your HTTP library turn that into a compressed form and send? Then it's HTTP2. Okay, so it should not matter. Your code should not change. It's the HTTP library at both ends changes, and it's just using a different way to communicate. Okay, so I don't know the answer to your question because that depends on what library you actually used. Okay, I would assume it's HTTP1 because HTTP2 is still only used in browsers and servers. I don't know whether it can be used in microservices. I'm assuming you can, but unless you used a HTTP2 library for lab 2, it's unlikely it was actually doing any of that. Okay.
That means that even if we say connection.open, if we call that multiple times, then also once the connection is made, it doesn't actually create an internet.
Right. The question is, if you use HTTP2 library and every time you make an HTTP connection, internally it should check that there is already a connection and it shouldn't make it. Okay, that's one way to write the library. The other way is to actually you keep track that you made the connection and you don't call it repeatedly. You just send the next request instead of opening a connection. Okay, there are multiple ways you can do it. I don't know which library does what actually, but yeah, either way, you don't want to set up a new socket connection. You want to send requests over the existing socket connection. Okay. Okay. So coming back to web services and SOAP. So as I said, web services are a way of using RPC, but you use XML to exchange information. And this is essentially a XML-based SOAP message. And one of the reasons this web service didn't become popular is that people found it was too heavyweight. Okay? To send a simple request and send this message, you have to send a very long XML document. You have to parse this XML document. Then you have to generate the response, send it back, and so on. Okay? So what people started doing was saying, already all these applications use HTTP. Okay? Why do we need to send XML document? Let's just use HTTP and encode the request as an URL. Okay? And any arguments we send as the body to the message, you can send JSON or some other way to send the argument. And I have all the information I need. I know which method I'm calling. I know how to pass argument. I don't need to send a complicated XML message to do this. Already HTTP is a lot more popular than using something like SOAP. So let us use HTTP as a way to make RPC requests. Okay? That led to RESTful web services Okay, and we talked about this again in lecture 2, but here is where we now try to understand what exactly it is given. So it is much more lightweight. Okay, that large message is essentially 2 lines. Okay, here is a message using SOAP that says, okay, I want to look up the price of a stock. This is the service I call, that's the ticker, is the price, and so on. And here, sorry, this is the REST version of it. So you basically just say get stock price, you name the argument, and you send it, and that's the response that comes. Okay? Here is the SOAP version of the same call. Okay? So I send a large XML document asking for the price of stock, I get a large response. Okay? So it is a lot more complicated what you could do using HTTP. And because HTTP was already pervasive, this is the way people write web services. Nobody actually uses the more old way to do this by writing the definition language using compilers and so on. You just use standard HTTP, you construct URLs, you send HTTP requests and get HTTP responses. Okay? So you are using HTTP as a way to make RPC requests. That's the way you want to think about all of these RESTful web services. So that's what you did in your lab. You're essentially sending HTTP requests to execute code on the server, right? So that's RPC. Okay, so this is what has actually become popular. Okay, so instead of doing heavyweight protocols, you use lightweight HTTP protocols. If you want to read something, you use a GET. If you want to create something, you use a POST. If you want to update something, you use a PUT. If you want to delete something, you use delete, but that's often not used at all. Okay, so much simpler than using SOAP, very close to what web applications already do. Okay, so here are examples. I'm going to go through them again. So you can write, this is a RESTful interface where you can use a get stock price / IBM, says get me the stock price of IBM, and it's sent to some host. Okay, and then you can say I can accept the response in different ways. This one is actually sending you the response as an XML document. You could have just sent a JSON object. Okay, what is sent is up to you. You define it. There is no standard there. Okay, so in your lab, you sent requests and responses and actually use JSON to pass information. You can use XML as well or any other format that you want. Okay, and as I said, this is much more compact than using SOAP to write this kind of application, and that is why it has actually become popular. Any questions on REST? Okay, I'm assuming you have some familiarity with it because you wrote code for it. Okay, this probably should have been an earlier lecture, but better late than never. Okay, so here is a quick comparison between SOAP and RESTful web services. Here, SOAP is designed to be a language, platform, and transport agnostic. You can write it in different programming languages. The client and the server don't have to have the same OS or platform. And SOAP is actually transport agnostic. Okay, you can send that XML or TCP. You can use other network protocols and so on. Okay. RESTful web services use HTTP. Okay, you can't change that. Okay, you are actually sending all your requests HTTP. Being said that, it doesn't describe what language to use. Okay, you can use Python to write your microservice and RESTful things. You can use Java. You can use whatever JavaScript and so on. Okay, and it's platform agnostic. Okay, but transport protocol is fixed, HTTP. Okay, this is designed for general purpose distributed system. You can have all kinds of applications that make calls from one another and so on. Okay. RESTful web services, one client, one server. Client makes a request to the server, you get a response. So the interface is point to point. Okay, you can have multiple clients accessing the server at the same time. The point is that you essentially have pairwise interactions, okay, just like standard RPCs. Okay. This is standards based. There's a long standard that says how do you write your interfaces, how do you compile it, and so on. RESTful web services they don't actually have a standard. Okay, there are guidelines. Okay, when I said you can design your own interface internally, some of you use REST, some of you use other things. But if you use REST, you could design it in many different ways because there's no one way saying that's RESTful. So long as you use the general guidelines, you can write RESTful web services in many different ways. Okay? So the simpler, less learning curve, as I said, tied to HTTP, more compact, because this is more heavyweight, okay, has better error handling and so on, because that's part of the standard, and you can extend your XML in many different ways. Okay? So many differences between the two, but as you know, the RESTful is where all of the work today is actually being done. Web services are considered too heavyweight for normal use, so very few people use it. Okay. Any questions on this? Okay. All right, so I'm going to introduce the next topic of web proxy caching, and then we will stop here today. Okay. So I already earlier in the lecture introduced this notion of a proxy server. Okay. Now, one mechanism that the proxies can be used for is for web caching or caching web content. Okay. So the idea here is you have clients that are making requests. Typically, you would basically take your URL and send it to the server that answers to that URL, which is the server over there. But let's say the server is distant; it's running on a distant cloud server. Okay? But there is a proxy server that is deployed close to the client. Okay? The proxy server maintains a cache, okay? And all requests are sent to the proxy server. The proxy server looks at the cache. So you say, I want www.cs.umass.edu/index.html. Okay? So if you make that URL, you'll come to the proxy, it'll say, do I have index.html from that server already cached? The answer is yes, you can immediately send that response back, because it's the same response the server would have sent. Okay? And if the proxy is closer to the client than the server, that response comes back faster. Okay? So you essentially reduce the load on the server, you increase the performance of the client. Okay? So you get both of these advantages. Okay? Now, there are some subtleties here. Okay? Let's say you cached a web page, okay? But the web page actually changed on the server. So you are now, let's say, instead of going to the UMass web page, you are looking for the main page of your favorite news site. Maybe there's a breaking news section is getting updated every few minutes. Okay? Whatever is cached is no longer up to date with what's on the server. So if you do not take care of the consistency problem, your proxy may serve stale content. It may serve an older version of the web page. Okay, you don't want that to happen. So cache consistency is important. If the web page changes, you better make sure the proxy knows something about this and does not serve stale content. Okay? So if you introduce any web cache, you want to ensure that consistency is maintained. Okay? We already talked about consistency for a variety of other things, storage and so on. Here is where we look at it in detail, but in the context of web applications. Okay? So we want to do cache consistency. Okay, but this figure here is actually showing another concept, which is if I ask for a web page, but what if the proxy does not have the web page? Okay, that's called a cache miss. Okay? If there's a cache miss, what do you do? Okay? There are two things you can do. One is go and get it from the web server, okay, and then you put it in the cache and return to the client, whatever it does. Okay, so the standard approach is if you have a cache miss, go to the server. Okay? What this picture is showing is another concept called cooperative caching, where you say rather than going to the server, is there a nearby cache that also has a copy of that? If so, maybe it's faster to get it from another cache. Here, as you can see, you ask for a neighboring cache, then going to the web server. Okay? This concept is called cooperative caching, where a set of caches cooperate with each other so that what the client sees is the union of all the content stored in the caches. Because you can make a local request, it can fetch that from another cache rather if it's not stored locally rather than going to the server. Okay? So this allows the cache to act as if it's logically a unified cache of all of the neighboring content. Okay? So that's called cooperative cache. So you can do one of these two things on a cache miss: get the content from the server or get it from the nearby cache. Okay? But what we'll talk about now, very briefly, is how can you maintain consistency of your cache. Okay? So here is the picture you want to keep in mind, because this was the old model where the browser sends a request to the server, gets a response. This is the new model we are now have. Okay, you have a cache sitting, proxy sitting in between. Browser sends a request. If it's a cache hit, response comes back. If it's a cache miss, okay, in this case, you're just going to the server. There's no cooperative caching we added yet. We will add that in a bit. Okay, so you get a request, send a response, put it in the cache so that any subsequent request can be served, send back to the browser. Okay, that's the picture you want to keep in mind. Okay, So let's talk a little bit about how are you going to maintain consistency of cached items. Okay, just talk about concepts. We'll look at the detail next. So what can we do if the web page changes at the server? How should the proxy deal with this? Interrupt. What are you interrupting?
For example, I have a connection to some web page. If something changes, web server can tell me something changed.
Okay, so you are saying that the proxy should have a connection to the server at all times. So if something changes, then you are going to tell the proxy something changed. Okay, so that if there are thousands of proxies, they will just have connection to the server. If nothing changes, that server connection will be wasting resources. But if things change frequently, you could do that. Okay, what other things can we do? But it is an option. We'll come back to that. It's not a bad option. Any other things you can do? How does the proxy know? Suppose that a request came, you look in the cache, it's a cache hit. Okay, how does the proxy know whether the content is fresh or not? Should it respond to the client or should it not respond to the client? Yes.
Can the proxy just check with the server the last update? Is there a particular guide?
Okay, so you can ask the server, right? So you can periodically check. So what you mentioned is exactly one approach where you do what is called pooling. You ask the server, okay, what was the last time the page was modified? There's actually a type of an HTTP request, which we didn't show earlier. We'll talk about it next time, called a conditional get. You basically say, here is the last time I got this page. Has it changed since? So you're asking, has it changed? Okay. So you can do what's called polling. You periodically check, I have this page, has it changed or not? If the server says not changed, you know it's fresh. If the server says it's changed, you delete it or get the new version of the page. Okay? That's called a polling based or a pull based approach. Okay? The proxy is pulling content from the server by polling. Okay? So if you know there's a pull, there must be a push. Okay? That's the opposite. Okay? So in a push based approach, the web server is going to keep track of every proxy and what pages are cached at those proxies. Okay, so when a web page gets updated, it looks at this table and say what proxies have this page, and you will send a message saying invalidate this page. Okay, this is a push-based approach. Okay, so there are these two techniques we will talk about next time. But the proxy can either poll the server and pull content, or the server can push invalidates or new content to the server. And we'll see there are trade-offs of either approach. And some approaches are better in some scenarios and others are better in other scenarios. But either way, we need something for the proxy to know that its content is actually still up to date, because you do not want to send old content to your users. They will just stop using the proxy cache, saying this is just old. You're sending me yesterday's news page. I want today's news, right? So that doesn't work. Okay. So we'll talk about all of these consistency mechanisms next time. So we'll stop here for today. Okay, thanks.